Hello everyone. In this lecture, we will learn how QAbstractDataType works and why they are used in data structures. In the overview of this lecture, we will have a look at definition of QAbstractDataType, types of QAbstractDataType, operations of QAbstractDataType, implementation of simple Q, implementation of circular Q, and with some list of applications. As we know, Q is an abstract data type. Queues are mostly used to prioritize data entries in a queue formation. A new data arrived in memory is always inserted from one end and removed at the other when needed. In data structures, this approach is often called FIFO, which stands for first in, first out. There are two well-known types of QAbstractDataType. One is simple queues, also known as linear queues, and circular queues. Circular queues, at the other hand, is an improvement over simple queue and more widely used in data structures. We will see why this is the case in coming slides. Simple queue has four common operations such as enqueue with data to enqueue data element to the queue array, dequeue to dequeue data element from the queue array, isEmpty to check if queue array is empty, and isFull if the capacity of queue array is filled and full. Initialization of simple queue in arrays can be illustrated as such. We need to have some type of array where we will store our queued elements, and we also declare front and rear variables which will hold indices of where front and rear data elements are stored. This is important. This way, we can efficiently know which data is the one that will be dequeued and which will be enqueued. In this following slide, we will see how enqueue method is implemented using simple queue on Java. When we call enqueue method with data, it will create a new data and check if our queue is full. In our illustration, it's not. So we skip the first if statement and proceed further. In second if statement, we check if our data is empty. As we know, isEmpty checks if our array doesn't consist of any data. In this case, it will return true and will increment the front value by 1. After the check, we increment the rear by 1 and say that the data will be equal to the index of rear in QArray. Let's see once again how enqueue operation would flow when we enqueue another data. We would see that first if statement would be skipped, and this time second if statement would also be skipped since our array is no longer empty. So this means front index wouldn't change. Again, we increment the rear by 1, and this time it would point to index 1, and the data would be equal to the index of rear in QArray. We can have third enqueue call to familiarize with the flow of enqueue operation. Next, we will have a look at dequeue operation in simple queue. When we call dequeue operation, we first check if our array is empty. In our case, it's not, so we proceed further. We create a temp variable and say that it is equal to the front index of QArray. This is done to know what element is going to be dequeued from our QArray. We check if front is equal to rear. This check is performed to know if we only have one element in the array. In this case, it's not, so we proceed further. We increment the front by 1, as it should now point to the next index since we are dequeuing an element from the array. And finally, we return the data element that is going to be dequeued. Peek operation in simple queues basically returns the front index of QArray. So this way, we know which element is the next who would be dequeued when needed. isEmpty method returns true if front is pointing to the -1. Is full checks if rear is equal to QArray length minus 1. In this case, rear points to the 5 and the QArray length minus 1 also equal to 5, so it would return true. Limitation is a big disadvantage of simple queue because of the number of data elements can be queued at one runtime. As we queue and dequeue in simple queues, we wouldn't be able to enqueue further when the last element will be enqueued. This is the case even if we dequeued some elements previously. This issue could be fixed by resizing the given array, but this also would lead to waste of space on the memory. From the described disadvantage, we can solve this issue by having circular queues. Circular queues can queue new data elements if there is space on defined array. Circular queues have 6 common operations such as enqueue with data, dequeue, peek, is empty, is full, and resize. Resize occurs when next element to be queued no longer has space in the queue array. This has nothing to do with the advantage of circular queues as resize happens only when array is full and we want to add additional data element to the queue. Advantage of queue arrays come from the capability of enqueuing new data element on the places where some data has previously been dequeued. Resize occurs when next element to be queued no longer has space in the queue array. But we should know that this has nothing to do with the advantage of circular queues, as resize happens only when array is full and when we want to add additional data element to the full array. Advantage of queue arrays come from the capability of enqueuing new data element on the places where some data has been previously dequeued. We will see this case in coming slides, and it will be clearer how circular queues are more efficient than the simple queue. At the initialization part of circular queues, we can see that there is no difference than simple queues. We have an array and also front and rear to keep track of indices stored at the beginning and at the end of the queue. Next, we will see how enqueue operation is performed in circular queues. In queue, we create data with defined type and check if our array is full. In this case, our array is not full, so we proceed further. At the second statement, we see that our queue is empty, so we increment our front by 1. Further on, we set our rear index with a simple formula of rear plus 1 divided by queue array's length and get the remainder as a new rear value. So, minus 1 plus 1 divided by queue array's length would return remainder of 0. So our rear will be at index 0. Now we get our rear as the index of queue array and assign data to that index. Let's see once again how we would enqueue another data in circular queue. This time we would skip 2 if statements as we neither have full nor empty array. So again, the formula is executed for rear variable. This time it would be equal to 1. And again, we get our rear as the index of queue array and assign data to that index. In the next slide, we will simulate some enqueue and dequeue operations for better understanding of how circular queues do work. Let's call enqueue method until we fill up the queue array. And dequeue some couple of data from our array. Now let's see how rear would point to 0 again using simple formula and validate our circular queue definition. As you can see, without resizing, we can enqueue as many data as our array size allows. Resizing, at the other hand, will be necessary when we attempt to enqueue additional data onto an already full queue array. We will see how resizing in circular queues do work in the next slides. But now, let's go on and enqueue more data to understand characteristics of circular queues. As you can see, how a basic formula is pointing the rear to the first index after an additional data is enqueued. This feature wouldn't be possible without resizing the array in simple queues. In the next slide, we will see how dequeuing works in circular queues. To dequeue a data from the circular queue, first we check if our queue is empty. In this example, our queue is not empty, so we skip the if statement. Temporary variable of temp is created to know what data element we are going to dequeue, or in other terms, delete from our queue. As we know that dequeuing only happens from front, so we take the front index of QArray and assign it to the temp variable. At the second if statement, we check if both front and rear is pointing to the same index of QArray. In our case, it doesn't, so we skip the if statement and increase the front with the defined formula. At the end, we returned temp variable, which will be the dequeued data element. To understand how resize works, let's simulate some enqueue operation to fill our array. If we would try to enqueue data to our full queue array, it would trigger the resize method, which would increase the size of our queue array. To achieve resizing, we do the following. First, a new local array is created. We named it as temp array for better understanding. In common, we increase size of the full array by double the length of that array. Next, we create local variable of I and set it to 0. This variable will be used as index in temp array to be able to copy elements with a do-while loop from QArray. J local variable is assigned to front of QArray as it is the first index of QArray. So this way, we know where to start copying data from QArray to temp array. Now, let's see how data would be copied from QArray to temp array using do-while loop. Now, our front would be pointing to 0 and rear would be QArray's length minus 1. After all setup is completed, we take temp array and assign it to QArray. Because of this override, we don't waste memory and just be having a new QArray with new size. Peek method basically takes the front index of QArray and returns it. IsEmpty returns true if front is equal to -1. In this case, it doesn't, so we skip the boolean function. IsFull method checks if rear plus 1 divided by QArrays.length reminder is equal to front. In this case, it doesn't, so we skip the boolean function. There are many applications that is using QAbstractData type. Some of them are CPU task scheduling and disk scheduling. In real-life scenario, call center phone systems uses queues to hold people calling them in an order until a service representative is free. FTP clients queue the downloading files from the server side. Users are queued to join server for the games with high load. Of course, those are just 4 examples and can be expanded to many. For example, FTP clients. They use QAbstractData type to queue downloading files from server side to your computer. Another example can be given by the games with high server load. They queue users after the server capacity is full. Queue is an abstract data type. Its implementation is user independent as long as it follows the queue methodology. Therefore, we should know that there are also different queues such as priority queues and doubly ended queues. In principle, they follow queue methodology but with different method implementations depending on the purpose that it should function. Thank you for your attention. Hope to see you in the next lecture.